Okay, well, we are ready to go here with sound. And also the previous lecture where we had that sound problem, we redid we redid the lecture to an empty house, time warp. You know, I did a lecture preparing for a lecture that was already done. Anyway, so we're all set. Now, I think today is one of those days where we have a homework assignment that's due, and the homework assignment I think was pretty extensive, and I think there's some pretty challenging proofs. So I don't know if you guys have tried them yet. I would hope so. Or are we, you know, in that mode where you're just going to wait until today and get it in by 5 and you haven't tried it yet, or what? So, questions about the homework?
Yeah. Can you do 9.9?
Can I do 9.9? Well, no, I will not do 9.9, but I can, yeah, but 9.9 is in fact the challenging one. That's,
Can we work on it together?
we can, I can maybe coach you through it a little bit.
Let's do it right now. Let's do 9.8 first.
But wait, did I? Yeah, that's right. I did assign 9.8.
Give us a hint for 9.8.
Oh, 9.8. You know, actually, 9.8 is it's not that it's not that bad. Yeah. If you do trading, right? You start with the left-hand side and get it to be the right-hand side. If you do trading, and then if you, yeah, 9.8 is not too bad. The hint for 9.8 is to do trading. And then after you do trading,
Which trading is like?
well, that's right, but you just take a look. And then after you get trading, try to pull something out. You know, if you can pull something out of the quantification, are you with me?
Yeah, sure.
So the hint for 9.8 is to use one of those tradings to get a couple of things in the body, and then once you have you know, an expression in the body, I think you can pull something out using some kind of a distributive.
9.6 is way easier.
Well, 9.
9.6.
Well, yeah, but you have to get it into the. Oh, I see. Oh, just 9.6 straight off, straight away. Oh, yeah, straight away. Yeah. Oh, that's a good one. Yeah, you don't even need trading, I guess. Yeah, you could use 9.6 right off. All right. Okay. So, but now, you know, like Cale said, I think the really challenging one here is 9.9. Now, did you see the hint? So let's talk about 9.9. It's for all x range R body P equals Q, that whole expression implies, in parentheses, for all x range R body P equals for all x range R body Q. Right? Now, did you see the hint in the, I think on the web page I said see the hint in exercise whatever, and there was a hint in the book. And did you see what that hint was?
Yeah.
What was it?
Use 3.62 on the whole thing.
Yes, and that's, I think, a really good idea.
We're using the whole thing.
Yeah, that's what he said. That's what the hint in the book was. Our author gave us that hint.
For 9.9.
For 9.9, yeah. So did you do that?
Yeah.
Okay.
Then
And now, yeah, so now you have this big, kind of long, complicated thing.
Which one was it? 3.9?
He said use 3.62. Because look, if you look back to 3.62, you have your sheets there. 3.62, it's in the exact same form, right? It's a P implies Q equals R. So now you have two, you have a big thing, you have some big expression equals some other big expression, right? And what we have to do is we have to get them.
Oh, you can use the.
We have to get them.
Quantification stuff.
Well,
Can't you?
yeah, you can use whatever you want. But so you have one big expression equals some other big expression, right? Now, what what do you have for that first big expression? It's what? For,
Want me to give you-
yeah, just tell me what you have.
It's all X range R, body P equals Q, and all X range R, body P.
You use range split.
Well, you have P in the body. What do you have? P
Equals Q,
equals Q.
and you have just P on the other one.
In the body. Wait, just read off exactly read off what you have. Exactly what you have after you did 3.62 on that whole thing.
Yeah,
All X,
range R,
range R.
body P equals Q,
Okay, body P equals Q. And then what? And then does it close the thing, or is it another one?
and then it's and then another one.
Is it, okay, so is it like this?
Yeah.
And then another quantification.
Yeah.
And so you have another quantification, what do you have?
All X,
Range R,
body P.
body P. But then,
That equals-
what, but then that whole thing equivales.
Yeah.
Oh.
That whole thing equals another whole great big thing, right? So here's what you have to do. Yeah. So now, so you have a big complicated expression here, and you have another big complicated equivales another big complicated expression here, right? So what you have to do is you have to manipulate this, and you have to manipulate this similarly to get them to equivalve the same thing, and then by 3.3 it'll be true. Are you with me? Is do you see that that's what you have to do based on what you have written down there so far? Is everybody? So this is a ... and this is a ... here, and this is a colon. P equals Q, and here's a ... colon, and what was this one?
P.
P, right? And then you have equivales ... and ... something similar to it, right? So this is the form of what you have it in so far, right?
Yeah, sure.
Okay, so what can you do? What's an obvious thing to do here?
Range split.
I don't think so.
Why not?
Because the ranges are. Why do you want to split the range? The range is. Are you with me? I mean, the range in both cases is R. How do you want to? There's nothing to split.
Use the and.
There's nothing to split, right?
You can't use the and to like group them together.
Oh.
That's
Now, what do you mean? Ands group them together.
Is that like distributivity? Yeah, just
Generalized, right? It's the general. Yeah. I think the generalized distributivity, right?
Something with a binary emphasis.
Yeah. Here, the one with
Yeah,
the general. 815, right?
Yeah.
So does 815 come into play here?
Yeah, do it twice.
Yeah, because it's a for all and it's an and. Yeah?
Yeah.
So I think you do that twice. You do that with this one,
Yeah.
and then you do that with this one also.
Bodies are the same. You just.
No. The bodies are not quite the same now. They're not. I don't think you're home. I don't think you're home free yet. Oh, the range is the same. Right.
Bodies are similar.
The bodies are. The range is the same. The bodies are similar. Yeah. Shoot, they're similar, but they're not.
Oh, we can do this. No fear.
No fear. Oh, I like that. We can do this. No fear.
Did not.
We are universal provers. Okay, so are we good?
Yeah.
Almost
Yeah, it's pretty good. Pretty good hint.
patient.
But we're still not home free. Why not?
Because we're not finished yet.
It's not,
Well, I know, but why aren't we finished? Why aren't those? They're very similar, but just not quite, right?
What do you? I don't know what you're trying to say.
3.5. It's 3.5
Ooh. Ooh, there, I think we're home free.
Oh yeah, that's a good one.
what are we at? 3, 3?
Kale just came through.
350 done.
Yeah, twice, one on both sides.
Yeah.
And then, yeah.
So you are allowed to manipulate just the body?
Yeah, you are, now look, when you do just the body, you are substituting equals for equals. You can always, Leibniz, you can always substitute equals for equals. Are you with me? Because that's Leibniz. Yes.
Which is,
Now, is that a cool proof, or is that,
it's like 2 lines.
well, it's more than 2 lines, I think.
No, it really is only 2 equals.
Well, it depends how many, like,
8.15.
And then,
8.15 twice.
No,
You're gonna do
362 is the first one.
Oh, yeah. Whoops.
yeah, that was a challenging one. That was good. All right, are we good?
You actually have to write down 3-3.
Yeah?
Was it 3? Hey. For the homework. Is that alright?
Do you want some more?
Forgot to write that.
Oh, you forgot to write the hint? Yeah, I can read that. I can read that.
You're not gonna screw me
No.
up with something?
Just if you're a little sloppy, I won't grade off for sloppiness.
A 16? Yeah.
Okay. What else? Is this the other thing? Oh, now remember I gave you that little supplementary for the instantiation one. Were you able to work through that one?
I think.
I gave you the worksheet, right, for that S.3. So that one was
You end
good.
up having like P with X replaced by Z with Z replaced by E, right?
Yeah, did you have
Like this double text.
yeah, and then a property of textual substitution. I mean, because provided you have to make sure your proviso is good, right?
I don't get why we had to do that. I don't know how this all of a sudden changed the proviso thing.
Okay, so we're talking about supplementary exercise S.3, and it's you're talking about the last step, property of textual substitution, because Z is not free in P.
No, that's. I mean, I get why we do that, but I mean, it's just this proof's kind of weird. There's a lot.
Well, yeah, and that's why I had this worksheet for you, because this is using concepts that we don't use very frequently in our other proofs, right? Because it has all these provisos, does not occur, this kind of thing. And that's the whole point of this whole proof, is that instantiation 9.13 has no provisos, yeah? So here, 9.13, this instantiation, there's no provisos. This says that if P is true for all X, that implies it's true for any one of them. No provisos, right? So the only way that you can do it correctly with no provisos is to go through this dummy renaming thing, and then doing this property of textual substitution, where if you have an expression and everywhere there's an A, you replace it with B, and then after you do that, everywhere there's a B, you replace it with A, you get back, it's the same thing, right? As long as there wasn't a B in the original expression. Is everybody clear on that?
Yeah.
Okay, so were we good for 9/11?
No.
That was a terrible day in our history.
Huh? Oops. Yeah, so 9/11 was another one. Body weakening, strengthening for all X, range R, body P and Q. That implies for all X, range R, body P. Well, wait a minute. Isn't this just like a one-step proof using strengthening?
Is it?
No. Because that's what you're trying to prove.
Oh, yeah.
Just because P and Q implies P,
What was the one we did on the board the other day? 9-7?
EO, was it? That was similar, where we had to pull it out? No?
Let me see. I think we used 8-15,
Yeah.
and then it's like already there. We're done.
Oh, yeah, for 9/11.
Oh yeah, for not, maybe it is just a two-stepper. Oh!
It's 8-15, and
It's,
pull it out,
yeah, you pull it, and then you have two big ones.
then you
And
weakening
then you can use
Oh,
weakening,
that's cool.
strengthening on the whole thing.
Yeah.
Right,
I
right.
like that.
Yes, yeah, the whole point of, yes, the whole point of the proof of 9.11 is to get it, is to use strengthening.
Or you start with the left side, get to the right.
Yeah, I would. I'd start with the left side,
You
get
have
it to the
say
right.
P and Q are Boolean.
Well, we know that they are because it's a for all, and the operator is, for all is and so the types have to be Boolean. Yeah? All right. Okay, I think you guys are doing good. Sounds like everybody's on board here. Okay, well, let's go on. Let's go on to existential quantification, which is what we looked at last time. And remember, this is kind of like our golden rule, in the same way that our golden rule defined conjunction in terms of disjunction. Our 9.17 axiom, generalized De Morgan, defines universal quantification in terms of existential quantification, right? Oh, sorry, it's the other way around. It defines existential quantification in terms of universal, right? Because all of the ones that we've done so far have been universal. So we're starting with universal. We have all those theorems, axioms and theorems, and now with this one, we have with this one axiom, our kind of, quote, golden rule for predicates calculus, we will define existential quantification in terms of universal. All right, so we talked about that one, 9.17 last time. Let's take a look at a few of these others. How about 9.18? Oh, I think, those are,
Proving something? No, we weren't.
well, I mean,
An axiom.
9.17 is obviously an axiom. We don't prove that. But how could you prove 9.18?
Using 9.7.
Obviously, prove it using 9.17.
Wait.
So what would you do?
Yeah.
How would you do that?
So it's just saying it doesn't matter where the negations are? As long as
Well, no. It says, what do you mean it doesn't matter? I mean, it says how it matters. It says if it's not the case that there exists an X over range R body not P, that's equivalent to for all X range R body P.
Those are ors, I forgot.
Now, how could you prove 9.18? I think I'm asking you to prove 9.18c on the homework. How would you prove 9.18a? Start with the what?
17.
Start with the what?
start with the left hand.
I would say so. Start with the left-hand side. Yeah?
With a not.
Are you with me? And then use what?
9.17.
9.17. Right? And then what would happen? If you use 9.17, can you do this in your head?
On the left-hand side?
On the left, we're starting with the left-hand
The
side.
double negation?
You would have not
Blah, blah, blah.
for all, blah, blah, blah. And not only that, but you would have in the body what?
Not P.
And then what you use what?
Double
Addition
12.
twice.
12 twice, and then you get the right answer.
And that would be the right-hand side.
I like it.
Is that cool? Now we can start doing these proofs in our head.
But for like
Huh? For 9.18a, does everybody see what? And then for 9.18b, same kind of
But
thing.
for 9.18b, can't we just use like the distributivity of negation over equivales and put it on the other side?
Oh, if you wanted to start with the whole side, you could do that. Yes. And then that would be,
It would be the axiom.
it would be 9.17. Oh. Huh? More than one way to skin a cat. All roads lead to Rome. Yeah. Okay? And then 9.18c, let's not say about how to do 9.18c because that's a homework assignment. But I think it's pretty straightforward. Okay, so 9.18c. Now let's take a look at 9.19. Let's take a look. 9.19 is a trading. 9.19 is also a homework problem. Okay? And what does it say? It says the way you trade with existential quantification is you can move the range to the body, but then it becomes a conjunction, right? So if there exists, what this says is that there exists an X, range R, body P. If there exists an X, range R, body P, that's equivalent to there exists an X over all of them. Body, R, and P. Does that make sense?
So we'd have to generalize De Morgan and then manipulate it over
Yeah.
to the universal.
Yeah. Yeah, actually, see, there's a, and bring it back. Actually, that's a good proof heuristic, what you just said. And this is very similar to what we did. We've done this kind of thing before when we did the golden rule. So here's the proof heuristic.
Heuristic.
You do not remember when we talked about proof heuristics? Like approaches to, the approach that you take to do a proof. So here's what you would, here's the proof heuristic that you just told us. And here's what you would do. You would eliminate, so the proof heuristic for existential proofs, right? So first what you would do is you would eliminate the existential using 9.17, right? And then from that, you have then you'll get it in terms of universals, right? So then you manipulate with theorems for universal quantification, right? In which you already know, there's already been proof. And then after you get it into that then what do you do? You
Bring it back.
Yeah, right. So you reintroduce this using, okay. So reintroduce existential using, again, 9.17. So, and this heuristic it's similar to what we did before. Same idea, but now it's, see how this stuff is just builds and you get the techniques and I think it's just great.
I think most classes build themselves.
Yeah, well, some do and some don't. Some topics do it. Okay, so that's 9.20 is an exercise, and then 9.20.1 is not in the book, but look at let's take a look at the difference. 9.20.1 is existential double trading. Now, if you have an existential double trading, what does that say? If you have there exists an X, range R, body P, you can simply do what? Flip them. But is that what happened with universal?
No, we had to not.
You had to, to do it universal double trading. Yeah, if you flip them, you have to knot them. That's kind of weird. When I first saw that, I thought, huh, it's kind of funny that way, isn't it? But when you think about it, it kind of has to be that way.
Oh yeah.
Of course it has to
There,
be.
it has to be.
The office says.
Because if it exists, if it exists, body range R, body P, it exists body, range P, body R, Either way, it exists, but not for all. You got to throw in those next. All right, so that's a pretty simple one. I didn't have you prove 9.20.1, but 9.22. Oh, 9.21 is a distributivity. 9.22 is a homework problem. Provided not occurs X in P. What is it? There exists an X range R body P. What does this say you can do? You can pull the P out with a conjunction, right?
And then put the range. in
And then put
body.
the range in the body. I think with this heuristic, I think these all look pretty straightforward. Oh, and 9.23, this looks very much like the one that we did in class for universal, doesn't it?
Yeah.
Because we pulled out,
Still getting the knots.
yeah. Right, yeah, we had that if the range is not everywhere false. Here what has to happen? The range has to be somewhere true. Yeah.
This is for all, where the other one was for and.
Yeah, and here this little proviso over here is that the range has to be somewhere true. There has to be a place for which it's true in order to be able to pull the or out, in order to pull the P out with the or.
Check that out.
Okay. And then here's another set. Oh, look at 9.24.
No.
There exists an X over range R, body false,
So zero.
equivales false.
Why don't they call it the zero of universal quantification? Or existential quantification?
It's related to like multiplication zeros.
What did we have before? For all X range R, body true was true.
Yeah.
Yeah, those are, I guess actually
Kind of
that,
zero.
yeah, it is kind of a zero.
Should email the book guy.
Well, I have actually changed some of the names on these. I modified them a little bit. I don't know if you noticed this, but the weakening, strengthening
Yeah.
ones, I made them explicit, just so that and the main thing there was to cement in our minds that and is strengthening or is weakening, Yeah. But anyway, so anyway, 9.24, I don't think I asked you to prove that. That's pretty simple, given that we know how to do the corresponding one for and. And then 9.25 is a range weakening, strengthening. Oh, now that's interesting, because 9.25 says that if you have Q or R in the range, it follows from there exists just one of them, R.
Yes.
Yeah? Okay. So that's a range weakening, strengthening. And then there's the other one, 9.28, 9.26 is a body weakening, strengthening.
Well, we can't use
Okay.
weakening strengthening on these, right?
Well, again, you have to get it out to the whole thing. Yeah. So there's a 9.
Isn't there any conjunctions?
Well, existential
Is
is
there like conjunction?
existential. The operator is or. That's where all of this stuff is coming from.
We use and for the other ones. Huh?
Mm-hmm.
Because universal is and.
Universal is and. Yeah. Okay. So 9.27 is a monotonicity of there exists. Okay. And 9.28 is I'm asking you to do that for the homework on Monday. On Monday, right? So 9.28 is existential introduction. Now this is interesting because what was the corresponding universal one?
1 point rule.
No, it wasn't the 1 point rule. It was this.
It was the truth.
It was instantiation. So now let's take a look at 9.13. Instantiation says if P is true for all X, then what?
It's true for one of them.
Then it's true for one of them. I mean, in other words, all men are mortal. Socrates is a man. Therefore, Socrates is mortal, right? So it's like, if it's true for all of them, then it's true for one of them, right? Okay, so now what is this one saying? What does the corresponding one say here? It's, wait, wait, where is
If
it?
it's true
Where-
for one of them, then there is one out of all of them.
Yeah, well, yeah, what this says is that if it's true for one of them, then that implies that there exists an X for which it's true. Now, are you with me? So you see how that, but well, it's the same kind of thing, right? If it's true for all of them, then it's true for one of them. If it's true for one of them, then there exists an X over all of them, for which it's true. Are you with me? I mean, it's kind of like the mirror. One is epsilon, this one is called epsilon, or existential introduction. So if you know that it's true for one of them, then you can write down this existential one. And 9.28, I am asking you to prove that on your homework.
I don't want to prove that.
Well, I think.
I don't think it's true.
I think they all are. Okay. So, let me go. Let's actually. You asked me the other day if I could give you an example of. No. I've got a nice example for you here. Let's go back. Let's take a look at trading 9.19 and 9.20, and let's compare this with universal trading, because you were asking, how does this trading, You were asking me when we started off with trading. You said, "Give me an example of trading," right? So I want to give. Let me show you that. Let's compare existential trading with universal trading. Compare existential and universal trading, because after all. I think it's important that we understand this, because after all, trading is the axiomatic, it's the whole thing starts with trading, right? That was the thing that defined universal quantification. It was the trading axiom, right? So here's our some, let me do this with an example. Suppose we have this, and I'll do this with a specific numeric example. There exists an I range 4 less than or equal to I less than 8, body I equals M. Now what is this saying? This is saying there exists an I in this range. So what are the possible values of I?
4, 5, 6, 7.
4, 5, 6, and 7. So there exists an I, 4, 5, 6, such that I equals M. Now, is I bound or free? It's bound. Is M bound or free? Free. So this whole thing depends on the value of M, right? This whole thing is either true or false depending on the value of M, right? So like if M is 5, this whole thing is true. If M is 11, this whole thing is false, right? Okay. But now, look at what trading says. This equals, by existential trading,
Trading.
Yeah, or you can just say 9.19. So tell me what this is by 9.19. Existential. No. What is this? What does this equal?
There exists an I.
There exists an I. And what was 9.19? Oh yeah, it is right there.
4 is less than or equal to I is less than 8, and I equals M.
Yeah, range what?
Oh, range true.
Range true. Are you with me? Range true, such that what? 4 is less than or equal to I is less than 8, then what? And I equals M. Are you with me? Now, is I bound or free? It's bound. Is M bound or free? It's free. And what is this saying? The truth of this depends on the value of M. If M is 5, then does there exist an X over, now assuming that this is a type integer. See, this is there exists an I of type integer, but in this range, yeah? So this says there exists an I out of this set 4, 5, 6, 7. There exists an I out of these 4 possibilities for which this is true. This says there exists an I over what? From minus infinity to infinity.
That fits both of those.
Yeah, but body 4 is less than or equal to I less than 8, and I equals M.
So it still has to be the same thing.
So it's still the same thing as this. But do you see what it's doing? This is saying over an infinite number. This is saying only out of these 4. But this is saying over an infinite number. But over an infinite number, this and this is the same thing as over just these 4 of that. Are you with me? So do you see? Yeah, you'll buy it. Great. Okay, so see, that's our... So this is kind of like, this gives you an example of, of the meaning of existential trading. But now how about this? How about this? Suppose we do for all I.
I have a quick question about the previous one.
Okay.
Could you, would that be the same as having the range be I equals M and the body being 4 is less than or equal to I is less than 8?
Yep.
Ah, well, and now you're talking about double trading.
That is double trading.
That is double trading. And the answer is yes. It would be the same as if I equals M is in the body and this is in the range. In fact, that would be a good example of double trading. Yeah, and that's why the double trading works without the negation. Yeah? Or it's an example of, okay? Okay, now check this out. For all I, 4 less than or equal to I less than 8, body I equals M. Now tell me. Oh, sorry. I'm going to change the example here. I less than M. I need to change the example to make it meaningful, more meaningful. Okay? Is everybody clear on what this says? This says for all I in this range. So now what is this? The numbers for I in this range are 4, 5, 6, 7, right? Now,
They are all less than M.
they are all, so this is it's 4 less than M, 5, and 5 is, and 6 is less than, and 7 is less than M. Well, if M is 13, then it is true that 4, 5, 6, and 7 are less than 13. But if M is like 5, well, it's true that 4 is less than or equal to 5, and 5 is less than or equal to 5, but what? Not 6 and 7, right? So the truth of this whole thing depends on M because M is a free variable, yeah? Does everybody does everybody understand the meaning of this? This is saying, for all I, 4 is less than or equal to I is less than 8. But now, what is this by universal trading 9.2? This equals by universal trading, which is 9.2. What is this by 9.2? Hello? Anybody awake out there? I see. I just woke somebody up. Okay, so all right. So for all I, range true. Now what does 9.2 say?
Not for.
Yeah, that was. Let's go back to our 9.2. For all. Yeah. Oh no, it wasn't the not. What was it? Range true.
Implies.
It was implies, right? So this would say 4 less than or equal to I less than 8 does what? Implies I is less than M. All right? Now what is this saying? This is saying, in this case, what this is saying is that if we just consider these 4 numbers, 4, 5, 6, and 7, then 4 is less than M, and 5 is less, and 6, and 7, right? That's what this is saying. Out of those 4 numbers. But now what is this? This is range true. So what this is saying is that over all the numbers from negative infinity to infinity, all the integers, from negative infinity to infinity, if 4 is less than or equal to I is less than 8, which are the numbers 4, 5, 6, 7, then I is less than M for all of those, right?
Yeah.
In other words, 4 is less than or equal to I is less than 8 implies, are you with me?
Depending on what M is.
Yeah, depending on what, because M is a free variable. And so do you see then that's the nature of universal quantification is if you limit it to this range, and you make this statement based on this I, based on this range R, that's equivalent to saying for all I over all of them, whatever the type of I is, in this case integer from negative infinity to infinity, this range implies this. That's the same thing. So there's your example. You asked for an example for trading. Yeah?
Pretty sure I did.
Well, even if you didn't, there you have it. So, put that in your pipe and smoke it. Okay. All right. Now, the next one, there's going to be a nice little proof that we're going to do on Monday that I don't think we'll have time to do today, so I want to talk about it and set it up.
The gold casket.
It's, no, it's not the casket.
The platinum casket.
Okay, so it's, here we have, it's I want to talk about 9.29. 9.29 is one that we really need to understand. So before we prove it tomorrow, I want us to understand what 9.29 says. So here's some notes
I buy it.
on 9.29. Now, the first thing about 9.29 is exchange of quantification. So let's just take a look at what it says. On the left-hand side, we have there exists an X, range R, body, and then what's in the body? For all Y, range Q, body P. Yeah? And now what's on the right-hand side? Instead of having there exists an X, range R on the outside, what do we have?
But it can only imply it.
Yes, it can only imply it. It can't go the other way. So what we have is on the right-hand side, we have on the outer quantification, it's for all Y, range Q, and then in the body we have exists X, range R, body P. Now, this turns out to be a difficult proof to do for general range R and general range Q. So what we're going to do tomorrow is we're going to prove it in a special case where the ranges are true. But we won't have time to get started with that proof. So what I want to do is I want to give you an example of this interchange of quantification. And this, by the way, you guys comes up a lot in math. I mean, this situation comes up a lot in mathematical reasoning. So the way I want to illustrate this is with an example. All right? And what we're going to do is, now tell me, what is a predicate? No. That's a proposition. A function that returns type Boolean. Right? So here's going to be our predicate. P. This is going to be about relationships. Loves. Loves X, Y. Means X loves Y.
True.
So, well, it depends on who X is and who Y is. All right. So does everybody agree that the type of X and Y is going to be people, a person, right?
Sure.
So this is going to be a person. You know, it could be me, it could be you, it could be whatever, okay? And then this loves is a predicate that is true if X loves Y and false if X does not love Y. Are you with me? So here's going to be our range R. Our range R are going to be X is an element of ABC. So ABC, these stand for people. Like this is like Adam, Bob, and Charlie. Okay? And then Q is going to be Y is an element of D, E, F, and G. This, by the way, this example is not in the book. You might want to. Well, Dolores, Ellen, Francis, Gail, whatever. Gina. Okay, Gina. Well, okay.
What was your E?
Ellen.
Okay, that's great.
Well, I mean, whatever. Okay, so, all right. Now, what I'm going to do is, I'm going to define this loves predicate with the diagram. Okay? So here's R. Here's the R's. The R's are A, B, and C. Okay, so this is A, B, and C. And the Q set is D, E, F, G, H. So this is D, E, oh sorry, F, G, oh there is an H.
You're pulling Helen out of nowhere.
Yeah, Helen. Helen.
You already have a Ellen.
Ellen,
Hillary.
Helen. Hillary, okay. G, H.
I like Ellen.
Okay,
She started a nation.
okay, now, here's what I'm going to do. I'm going to put a line, I'm going to put a line from A, I'm going to put a line from a person here to a person here for everyone who loves whom. So Adam, this line means Adam loves Dolores, and this line means Adam loves.
He also loves Charlie.
No. I'm just putting. I'm telling you. This is who these people love. Okay. So Adam loves A loves D. A loves F. B loves E, F, and G. B loves E, F, and G. Are you with me? And C loves D, E, F,
He's a hoe.
G, and H. Right? Okay. So let's just jot that down. Let's just jot that. Who loves whom? So A loves D and F. B loves E, F, and G. E, F, and G. And C loves D, E, F, G, and H. D, E, F, G, and H. Are you with me? Now, what I want to do now is write down both sides of 9.29.
Okay.
Right? And you tell me what's true and what's not. So, what does this mean? There exists an X, range R, body for all Y, range Q, body P, where P is that loves predicate. What is this saying? There exists whom? Who exists?
From A to C.
There exists somebody in here, right?
Yep.
Is everybody with me? There exists an X in this range, A, B, C, yeah? Such that for all Y,
Out of all of the women,
of all the D, E, F, G, and H in here, that X, there exists an X such that X loves Y. What is this saying?
true.
Yes.
It is true because of why? Because who exists? Because C exists. But what this is saying is someone in R loves everyone in Q. Are you with me?
Okay.
Someone in R loves everyone. Loves
C is actually Christ.
everyone
Everybody.
in Q.
He does. But
Now, what about, but now look, and in this particular example, it happens to be true. But what happens if we flip it around? What happens if, if we say this?
Everyone in Q.
For all Y, for all Y
all of the women.
in Q, there exists an X in range R that this predicate is true, right? Oh, I forgot the print around this. Are you with me? Okay. Now, in English, what is this saying?
Everyone in Q.
Everyone in
In
Q
is loved by someone.
is loved by someone. And now, in this case, it happens to be true. Okay.
By the same someone.
No, not by the same someone. Not by the same someone.
There exists.
That's why this is an implies and not an equivalence. Okay? So what this is saying is that everyone in Q, everyone in Q is loved by
We'd run out of-
someone
We have to make up very interesting variables.
in R.
Jesus praise God.
Now look, you guys.
The world.
Now look, you guys. Tell me. Now, can you see then why the implication goes one way and not the other? In other words, if someone in R loves everyone in Q, then what? Everyone in Q is what? Loved by someone in R. But look, what if C does not love E?
Well, then the first one's not true anymore.
Well, no, wait a minute. What? Yeah. What if C does it? What if C?
Then someone.
Okay, but then what happens? Then it's not true that someone in R loves everyone in Q.
But everyone.
the other
But still, everyone in Q is loved by someone in R.
False implies true.
That's true.
It's still true.
So the thing of it is that if this is true, then this is true. But it's not the case that if this is true, it's necessarily that's true. Are you with me?
If the other one's false, then that one's going to be false too. So it'll always be true. That's why it is.
Well, it's contrapositive.
Yeah.
What you just did was the contrapositive on that. Yeah? Things to think about, right? Okay, so see you next time.